So, as a next step we want to look at, so the space of Riemann integrable functions are inside the class of Lebesgue integrable functions. And here is a observation which one can observe from the proof of this theorem, that if a function is Riemann integrable, then it must be continuous almost everywhere. So, to conclude this observation from the proof itself, basically what we have to look at is that the function f is the limit of those step functions, right. There is the limit of the step functions. So, if we leave aside those partition points, so we can remember we concluded that f is limit of those step functions phi n's and psi n's. So, with that we concluded, namely that here. So, we concluded that this is the fact that we proved in our theorem, that the limit of the step functions phi n and psi n is f of x, right. So, that almost everywhere. So, almost everywhere psi f is limit of psi n's, and psi n's are piecewise continuous functions, they are step functions. So, the points where psi n's may not be continuous are possibly the points of the partition points of p n's. So, if we pull together all the points, partition points, they will be at the most countably many, and if you remove them along with this almost everywhere set. So, outside a set of measure 0, this function f will become continuous. So, I am just indicating the possibility of a proof of that. So, those interested probably should look into the textbook. And in fact, the converse of this theorem is also true, namely that if f is a bounded continuous function, which is bounded function which is continuous almost everywhere, then f is Riemann integrable. So, that means there is a characterization of Riemann integrable functions in terms of continuity, namely a function f is Riemann integrable if and only if it is continuous almost everywhere. So, we are not given the proof of this. So, those interested probably should look into the textbook as mentioned above, an introduction to measure and integration, in which the complete proof is given. But what we wanted to indicate, that the proof of the theorem, proof of one part of the theorem, namely for a Riemann integrable function, it should be continuous almost everywhere, is already included in the proof of the fact just now we proved that Riemann integrable implies it is Lebesgue integrable. So, that is one part of the properties of the space L 1 A B, that R A B, the space of Riemann integrable functions, is in L A B. Now, let us look at a metric on L 1 of A B. So, recall we have already shown that L 1 of A B is a vector space. We showed that if f and g are integrable functions, then f plus g is integrable, f into g is integrable, alpha times f is integrable. So, it is a linear space. So, it is a vector space over the field of real numbers. So, on this we are going to define a notion of a magnitude. So, for a function f in L 1, we define its what is called the L 1 norm of f to be the integral of the absolute value of f of x d lambda x. So, this is called the L 1 norm of the function f, which is in L 1. So, clearly, it is a number, finite number, because f is integrable. So, this right hand side exists and is finite, and you are integrating a non-negative function. So, the first property, namely the norm L 1 norm of a function is bigger than or equal to 0 for all functions f in L 1 of A B. So, that is obvious. The second property, namely supposing this function f is 0 almost everywhere, then clearly integral of the function will be equal to 0, that we have already observed. So, norm will be equal to 0, and conversely, if the L 1 norm is equal to 0, then the function absolute value of f of x being a non-negative function, its Lebesgue integral 0 that implies that the function must be 0 almost everywhere. So, the second property, namely the norm is equal to 0 if and only if the function is 0 almost everywhere. And the third property, which is that if you multiply the function f by alpha, the norm of alpha f is equal to the absolute value of alpha times norm of f. And that is obvious, because in the definition, if you replace f by alpha f, then this being a constant, the property of the integral. So, the integral of alpha f is equal to mod alpha times integral mod f. So, that gives you the property that the L1 norm of alpha f is equal to the absolute value of the constant with which you are multiplying alpha mod alpha times norm of f1. And finally, the triangle inequality property, namely if f and g are integrable functions, then we have already shown that f into g is also a integrable function, and integral of the absolute value of f plus g will be less than or equal to integral of absolute value of f plus integral of absolute value of g by the triangle inequality of the numbers. So, that will give us that the L1 norm of f plus g is less than or equal to L1 norm of f plus L1 norm of g. So, these are the properties of this magnitude or this norm of f1. At this stage, I just wanted to point out that this is very much similar to the Euclidean metric or Euclidean norm on Rn. See, on Rn, for a vector x with components x1, xn, we normally define the norm to be equal to, we can take the norm to be equal to sigma mod of xi I equal to 1 to n. So, this is what is called the L1 norm on Rn. And now, so what we are saying is that if x is a vector with n components, then this must be the norm, L1 norm. Now, treat a function f defined on an interval a b to R. So, treat as a vector with components, with as many components as points in a b. So, I want to treat this f as a vector with components, as many components as points in a b. So, for a point x in a b, what is the xth component of f is nothing but f of x. So, you can treat f of x belonging to a b as a vector. So, if you treat that way, then what is the L1 norm of f you would like to define? So, keeping in mind, so take the absolute values of the components. So, take the absolute value of the components. So, this is the component, take its absolute value and you want to sum it, and the summation is nothing but integral d lambda. So, this is in that sense, this is a perfect generalization of the ordinary L1 norm on Rn. So, the only problem in this is that we do not have the property that if L1 norm is equal to 0, if and only if f is equal to 0. So, only we have got that the L1 norm is equal to 0 if and only if f of x is equal to 0 almost everywhere. But let us keep in mind that the L1 norm does not change if we change the function on a null set, on a set of measure Lebesgue measure 0. So, with that observation in mind, from now onwards what we do is, in L1 of a b, we identify functions which are equal almost everywhere. So, if two functions are equal almost everywhere, if f and g in L1 are same, are equal almost everywhere lambda, then we treat these functions to be as same. So, with that understanding, this becomes a metric d f g, which is equal to norm of f minus g, L 1 norm of f minus g becomes a metric on L 1 of a b and is called the L 1 metric. And the fact we wanted to the observation I want to point out is R A B is a subset of L 1 of A B, and so R A B as a subspace with L 1 metric is not complete in the L 1 metric. So, that is an observation which you should read from that textbook already mentioned. So, and this was one of the defects of Riemann integral that motivated the development of Lebesgue integral, namely the space R A B under the L 1 metric is not a complete metric. So, this is not a complete metric under the L 1 metric. So, but there is a theorem, namely every metric space can be completed. So, there is an abstract theorem in metric spaces that if every metric space can be completed. For example, you look at the set of rational numbers that is not complete under the usual distance of absolute value as a distance, and its completion is the real numbers, and that is the important property of real numbers, that it is complete under that metric. So, similarly, R A B under the L 1 metric is not complete, and there is a abstract theorem that R A B can be completed, it can be put inside a complete metric space. What we are going to show is that completion is nothing but L 1 of A B. So, we are going to prove that L 1 of A B, the space of all Lebesgue integrable functions on A B, can be realized as the completion of the space R A B under the L 1 metric. And this we will be doing in two steps. One, we will show that in the L 1 metric the space L 1 A B is complete, that is one, and it to be a completion of R A B, we will show that R A B sits inside L 1 of A B as a dense subset. So, R A B sits inside L 1 of A B as a dense subset in the L 1 metric, and L 1 is complete. So, that will show that L 1 of A B is a realization of the completion of the space R A B. Like rationals are dense in the real line, reals are dense, the field of real numbers is complete. So, that is why we say that real numbers is the completion of the field of rational numbers. So, in the similar way, we want to prove that L 1 of A B is the completion of the space of R A B. So, that means we want to prove that L 1 A B in the L 1 metric is complete and R A B is dense in it. So, the completion part is called the Rees-Fisher theorem. So, the Rees-Fisher theorem states that L 1 of A B is a complete metric space in the L 1 metric. So, let us look at a proof of this. So, the proof that to prove that it is a complete metric space, what we have to show? We have to show that every Cauchy sequence f n in L 1 of A B converges to a value in L 1 of A B. Every Cauchy sequence in L 1 of A B is convergent and convergent to a point in L 1 of A B. So, that is what we have to show. So, for that, so let us will to show that. So, this is what we have to show, that there exists some function f in L 1 of A B such that f n minus f L 1 norm converges to 0 as n goes to infinity. So, this to prove this fact, here is an observation. What we will show is, it is enough to show that there exists a subsequence of f n which is convergent in L 1 norm. So, what we will show is, to show that f n is convergent in L 1 metric, it is enough, f n is a Cauchy sequence. To show that a Cauchy sequence is convergent, it is enough to show that there exists a subsequence of the sequence Cauchy sequence which is convergent. That will prove that the sequence is convergent. So, to do that, so we have to produce a subsequence of f n which is convergent to a function in L 1. So, let us look at the first step of our construction. To construct that subsequence, we are going to use the Cauchiness of the sequence f n. So, f n is Cauchy. So, the first step is that saying that the sequence f n is Cauchy implies that I can pick up a subsequence f n k of f n such that the norm of f n minus f n k's is less than 1 over 2 to the power k for all n bigger than or equal to n k. So, to do that, we start with, so what is Cauchiness means? So, saying that the sequence f n is Cauchy, saying that the sequence f n is Cauchy, that means it is same as for every epsilon bigger than 0, there exists some stage n naught such that norm of f n minus f m is less than epsilon for every n and m greater than or equal to n naught. So, that is Cauchiness. So, to start our construction, so take epsilon equal to 1 and find n 1 such that norm of f n minus f m is less than epsilon equal to 1 for every n and m bigger than n 1. Okay. So, in particular when m is equal to n 1, that will give me, so that is f n minus f n 1 will be less than 1 for every n bigger than or equal to n 1. So, that is the first stage. Okay. So, now suppose n 1 less than n 2 less than n k have been constructed, have been found. So, now use Cauchiness. So, find n k such that, so how do I find n k? So, I will find n k such that norm of f n minus f m will be less than 1 over 2 to the power k for every n and m less than n and m bigger than or equal to, find n k plus 1. So, there is the next one we have to construct n k plus 1. So, I will find n k plus 1 such that n k plus 1 is greater than n k and this property holds. So, then for m equal to n k plus 1, I will have f n minus f m k plus 1 will be less than 1 over 2 to the power. So, I can put it k plus 1 also, that does not matter, k plus 1 for every n bigger than or equal to n k plus 1. So, by induction there exists n 1 less than n 2 less than n k less than so on, such that norm of f n minus f n k is less than 1 over 2 to the power k for every n bigger than or equal to n k. So, that is step 1, we do that. So, once that is done, we go to step 2, and the step 2 is showing that this subsequence that we have constructed has the property that the sum of the L 1 norms of f n 1 plus the L 1 norm of 1 to infinity of this is finite. Okay. So, that the sums of the L 1 norms of f n 1 plus the L 1 norms of f n j plus 1 minus f n j, j 1 to infinity, that is all finite. And that that follows from the fact that, see, just now we looked at this. So, that means norm of f n k plus 1 minus f n k is less than 1 over 2 to the power k. Okay. So, if I specialize n to be equal to n k plus 1, then I have this property for every k. So, that implies that if I look at the summation, so norm of f n 1 plus sigma norm of f n k plus 1 minus f n k, k equal to 1 to infinity will be less than or equal to norm of f n 1 plus sigma 1 to infinity 1 over 2 to the power j, and that is finite. So, that will prove that the required property step 2, namely sums of norms of these quantities f n 1 and this is finite. Once that we have that, now I can apply my series form of the Lebesgue dominated convergence theorem. So, as a step 3, as a next step, I want to conclude that if I look at the corresponding functions f n 1 x plus summation j 1 to infinity f n j plus 1 x minus f n j x, then this series is convergent almost everywhere. Okay. So, that is precisely follows from the series form of the Lebesgue dominated convergence theorem. So, if I look at this series, then I know that L 1 norms of this series is finite. So, that is precisely the perfect situation where the series form of the Lebesgue dominated convergence theorem applies and says that these functions this series must converge almost everywhere. So, this sum must exist almost everywhere, and if we denote the sum by f of x, then f of x equal to this exists almost everywhere, and it also says that that function is actually a integrable function, and integral of f is equal to integral of f n 1 plus integral of the sums of the corresponding series. So, these integrals of f is equal to integral of f n 1 plus this series. So, we have located a function f, and now is only to claim that the difference f minus f n j goes to 0, that the f is the limit of that subsequence. So, let us look at, so note that if we look at f minus f n j, that is precisely equal to summation j equal to k equal to j let me n j. So, that means k equal to n j plus 1 of f n k minus f n k minus 1. So, the difference between f and f n j is nothing but the tail of the series with the terms f n k minus f n k minus 1. So, norm of f minus f n j L 1 norm is going to be less than or equal to summation norm of f n k minus f n k minus 1 from k from the stage n j plus 1 onwards, and that is the tail of the convergent series geometric series 1 over 2 to the power j. So, that goes to 0 as j goes to infinity. So, that will complete the proof that hence the f minus f n j goes to 0 as j goes to infinity. So, that will prove that the subsequence f n j is convergent. So, let us just go back to the proof once again. Basically, the proof requires one observation, namely to show that a sequence, a Cauchy sequence is convergent. It is enough to produce a subsequence which is convergent, and that subsequence is produced in such a way that by using the Cauchiness we produce that subsequence with the property that the norms of the consecutive terms of that subsequence are less than 1 over 2 to the power j. Once that is done, we apply the series form of the Lebesgue dominated convergence to conclude that the sum of f n 1 x plus summation f n j plus 1 x minus f n j that exists almost everywhere, that is a integrable function and the integrals converge. And once we have that, it is obvious that norm of f minus f n j goes to 0, because once we subtract that, the remaining thing is a tail of the series 1 over 2 to the power j, and that must go to 0. So, with that we proved the Riesz-Fischer theorem. So, today we analyzed two important things, namely one, that the space of Riemann integrable functions is inside the space of Lebesgue integrable functions, Lebesgue integrable on the interval a b, and the notion of Lebesgue integral extends the notion of Riemann integral. So, that was one property, and the second property we observed that the space of Lebesgue integrable functions on the interval a b under the L1 metric is a complete metric space. So, and we will continue this analysis tomorrow, and we will show that the space of Riemann integrable functions, which is inside the space of Lebesgue integrable functions, sits inside as a dense subset, and that will prove that L1 f a b is the completion of the space of Riemann integrable functions. Thank you.